You are a man. Awesome. All right. Where are we at? Remind me of some stuff. I cleaned this off because I want to see what we remember, or at least what we wrote down. Because I want to build off it to kind of get. We're going to get like more specific and more specific and more like over these next few days. We're going to work on this exponential stuff, learning how to apply it to kind of different situations. So, in general, what do you know? Anything and everything. Give me one thing.
For what?
Anything that we've done so far that has to do with exponential functions. Paige, what do you got?
The formula would be a times b to the x plus c.
Cool. And so what should I put like over here?
F
F of x. Can I put g of x?
Yeah.
Y? Doesn't matter what I put. Cool. Somebody tell me about that equation. Like, tell me what one of those things mean. Yeah. Okay, and in addition to that, maybe we can kind of fill this up a little bit. What is that point gonna help us figure out? The starting point, yeah. Because what you're gonna see, I mean, I know we've talked about it a little bit. In general, when we start actually getting to specifics, this won't even be there. That's just gonna be 0 most of the time. Starting at 0 kind of makes sense. So really, it's just gonna, like, our starting point most of the way will just be that A value. Cool. Something else. Base is base 9. Now, today we're gonna start getting into more specifics about that base. But tell me about what like the size of that base, just based on what we know so far, how that can get us to understanding like when it's gonna go up from left to right and when it's going to go down. Okay.
So for growth, b is going to be bigger than 1.
Okay.
And then for decay, b is going to be bigger than 0 but less than 1.
Bigger than 0 and less than 1. Good, nice, bro. Because if we plug in 1, it's just 1 forever. Plug in 0, it's just going to be 0 forever. And if we can't even bother with negatives, because it just doesn't make any sense to bounce back and forth. So. And that's going to be a really big focus for us this week, is kind of getting really specific with just this. Like what's going to be inside there, raised to that power. And we're going to start messing with that. And like base, like 3 or 1/2 or 2 or 1 point, like we're going to start messing with that number and coming up with some formulas and some ideas that'll help us apply this. Cool. What else? Anything else worthwhile? Yeah, there we go. Our vertical shift. Just kind of going back to transformations. Cool. I was about to write the word transformations. Vertical shift. Cool. But I'll just kind of move the whole graph up or down. But C is definitely an important number for us. In terms of what we learned, I think it was Friday. I think one of the most recent things that we talked about was a line that's always going to be the equation just y equals c. It's not really part of the graph, but it helps kind of guide the graph from one side or the other. Remember what that was? Kind of a new word for us. Paige. Nice, said it well too. Asymptote. What is that?
It's a line on the graph that never approaches but never.
The line that a graph approaches, so it's going to get closer and closer and closer to it, but never reaches. And never is. You'll see next year. We can cross some horizontal asymptotes depending on what the function looks like, but not with exponentials. So for us, we're never ever going to cross that line. And usually what we'll do when we're looking at a graph, let's say it kind of looks like this. What we'll do is we'll draw on that line and we'll just kind of dash it. All right, so there is your asymptote right there. It's a line that's going to get really, really close to on one side, not both, just one side or the other. You know, maybe it goes, maybe this is growth in black there, or maybe it's, you know, maybe it's decay and kind of looks like that. Those are two different functions. The black one's growth, the purple one's decay. But either way, we kind of get closer and closer and closer to that line, but we're never actually. Sweet. Okay. So I want to start kind of getting more specific with this. I think that's pretty good, right? Knowing this is going to help for sure, right? Whether we want to get bigger, we want to get smaller, because that'll kind of adjust things as we go. Knowing that the vertical shift is there, but usually we're just going to do y equals 0. It's kind of nice to just have, you know, positive numbers only, never have to worry about negatives. And then that'll kind of adjust our starting point, because I think our starting point was like 0, comma a plus c, like our y-intercept, right? Our y-intercept right there, whatever that is, was a plus c. Well, if c is 0, then sweet, it's just a. We don't have to worry about too much. Because the thing about exponential growth and decay is it works really, really well with modeling like actual stuff that's happening out there, right? Break out of these four walls, get outside, start talking about the way things happen naturally in the world, whether it's population growth or we're talking about bacteria or whatever. Like there's a million, 1,000 million, 100 million. There's so many different ways to use this as a really good guide. And that's what I want to start exploring today, tomorrow, and kind of moving forward a little bit, is how to deal with this. Now, I could go into a lot of detail as to where this stuff comes from, why the formulas work out the way that they do. We can discover them together. I could spend a whole like semester on exponential functions. But we've got like 2 or 3 weeks. And so if you'll let me, I'm just going to give them to you instead of like building them together. But know that we could walk through this really slowly. Instead, we're going to walk through it a little bit faster. We're going to do stuff together. So knowing what we know, I think what that can get us to is some pretty interesting kind of stuff. So let's do it. If you didn't have any of that stuff down over there, make sure you write that down. But everything from here on out will be me like working with that function, the a times b dx plus c. But I am going to start changing some of the notation a little bit, like a, b, and c. I'm going to start messing with those letters because I want to attach some words to them. And I'm going to use like the first letter of the word and that's going to be the variable that I choose. Okay. And so the first one that we're going to start with, this part's new, is dealing with exponential growth and decay, but picking some bases that might be just a little bit, I don't know, just not like 2 and 3 and 5 and 10. Like what if I don't want to go up that fast? There's not a lot of things in this world that double. That's really, really quick. Or triple, right? Base of 3, or quadruple, base of 4. Usually things don't grow that fast. You look at like the population of Ponderosa and how that changes from year to year. Like we go from like 1,350 kids to 1,385. And then 1,400, and then 1,425. Like we're not growing all that fast. We're still growing, so I still want a base that's bigger than 1, but it's nowhere close to 2. We don't go from 1,400 to 2,800 from year to year, ever. We don't do that. It's just not the kind of thing that happens naturally. Now, sure, like you talk about like the changing of like the size of, a person growing, inside his or her mother's stomach. That can change way faster. Right? You talk about like cell multiplication, but in general, things are kind of slow, right? Things grow on the slower side. And so as nice as it is to have nice whole number bases, 2s, 3s, and 5, whatever, it's not realistic. Our base is usually pretty close to 1 on either side. But it's going to be like 1.1, 1.2, 1.05, like 0.8. Like we're going to be really, really close to 1. And so an easier way to understand that, I think, instead of talking about like whole number bases, is to deal with percent growth and decay. You know, from year to year, the population of Ponderosa goes up 3%, 5%. Right? The value of my car goes down 8% per year. Like that kind of thing is a lot more realistic. The value of my house has gone up 14%. Now, kind of dealing with a base that's pretty close to 1, maybe just a little bit bigger, a little bit smaller. And so what I want to do is I want to adjust our formula a little bit to kind of deal with that. Okay, and so you're going to see me change the F, A, B, and C. I'm going to use different letters because I want to name them. Okay. Now you heard me say it a lot. You know, the population of Ponderosa grows by 5% per year. The value of my car goes down 14% per year. My savings account increases by 1% per month. The thing that's changing is not just any X. It's time. Time is the variable that no matter what, whether you're looking at that clock or not, it's going to go up at the same rate no matter what. Right? I don't have to do anything for time to change. It happens independently. Okay? And so I'm not going to call it f of x. It's going to be related to time instead of any random x. So inside here, like f of whatever, I'm not even going to use f. I'm going to change this. But inside here, it's not x. It's t. Okay? And t is time. Your variable is going to be some time measurement. Maybe it's hours or days or months or years or whatever. Seconds, milliseconds, who cares? It kind of depends on what makes the most sense. But the thing that I care the most about usually is how much of something I have after a certain amount of time. You know, how much my car is worth, how much my house is worth, how much my investments are worth, how many people there are, how many animals there are. You know, think about like population growth doesn't just have to be people. And so instead of F, I'm actually going to use the capital letter A, okay, for amount. After however much time has passed. And it's really like a final amount. What's nice about this setup is if I can figure out the formula and you give me all the missing pieces and I can plug stuff in, I'll know like what the final amount is after a certain amount. Okay? So it's not f of x. I'm going to call it a of t. The reason I'm capitalizing the a rather than using lowercase is that we don't get it confused with this a right here. Now, I'm not even going to have an a in this formula at all, but just so that we're super obvious that we're talking about something else. Okay, I need like a starting point, and I need a base. That's really all I need. C is going to be 0. Okay, we're not going to move stuff up or down. We're just going to leave C alone. We're gonna let C be 0. So really, I just need like something here and then something right after. And of course, up in the exponent will be that there. But I'm not going to put a because that might just be a little confusing. Instead, I'm going to use a letter that means like the starting amount, but the letter S kind of looks like a 5, so I'm not going to use S. And if I said amount, it would be kind of confusing because I already have an A in there. So I'm going to use a word that means like the starting amount, but it's a word you might not have ever heard of before, unless you like have a background in some of this stuff. And it's called the principle. Spelled like principal outman, same thing. So I'm going to use the letter P. Okay, it means principle, but it's not the same kind of principle definition like principal outman. But just starting out. Okay, so and that would make sense because that's always been our start. Okay, in here we've got some stuff, and you're going to leave some space there because we're gonna have more than just a single number in there to start. But up in the exponent is going to be t. Right there is time. And that's the only thing that is going to change. That's the only variable in here. So from problem to problem, like we're going to figure out, okay, what's the principal? We're going to figure out what goes in here, and this is going to be numbers. But if I was plugging this in my calculator, and I was going to y equals, up here would be the answer. These all just be numbers. The thing about the inside, how to create a base that I want, right? If they ask me the question, and maybe we'll answer this one first, and we'll kind of think about what goes in there. Money is always an easy one to start. Let's say you start with $1,000 or something. You graduate from high school and total up all your graduation presents, you get $1,000. So I'll take it. Okay? I'll take it. Let's say you get $1,000. This is a nice easy round number. But you don't need it. Let's say this is money you want to save, maybe save up for a new car or put away for college or whatever. And so you put it into an investment, and let's say it makes you like 5% interest. And we'll talk a little bit more specifically about how interest is going to change. We're actually going to extend our percent growth and decay formula here in a couple of days to deal with the reality of interest. I'm going to simplify it a little bit. So I guess the question is how much money do we have after 1 year? Let's say it's a 5% interest per year. How much money do you have total? So I guess the question is like, what's 5% of $1,000? $50, right? Because if it was 100, it'd just be 5, right? So add a 0, okay, add a 0. But the answer to this question is not $50. How much total do I have? 1,050. And so, like, I don't want to come in here. First of all, don't write this yet. I don't want to, create a setup where this is the number 5. That's times 5. That's me going and having $5,000 after a year. That's not what's happening. What's 5% as a decimal? 0.05, because it's like 5 cents. When you think per cent, it's, let me ask you this. How many cents are there in a dollar? How many years are there in a century? Still 100, right? Percent really just means out of 100. Per cent out of 100. So 5% in my mind, I think 5 cents, like 5 pennies. How do I write that? 0.05. Well, imagine, don't do this yet, but like imagine just putting that there. Is this number bigger than 1? No, that's not good, right? I want my money to go up. And if I just put the rate, let's call it the interest rate, if I just put the rate in there, that is heavy decay. I'm only gonna get myself my $50. I want to figure out the final amount. And so what we're going to do to have this formula work for us, and now you can write this down, is we always want to start with the number 1 and adjust up or down based on whatever our rate is. So this is literally just the number 1. It's not a variable that we're going to plug anything in. It's just the number 1. What I'm going to do right after that is I'm going to write the rate as a decimal. But I want to give myself a chance for it to go up if it's growth or go down if it's not. And so if I put like the R right there, let's say for rate, so call that R, I would love to put a symbol in between those two that will help me, like in general, like I have a formula that works whether we're going up or down. Is there a symbol that we could put right here that means add it if we're going up or subtract it if we're going down? There it is. Awesome. Now we're going to pick one though. We're going to pick one. It's either going to be plus or it's going to be minus, depending on the setup, right? And there's different kind of things that grow exponentially versus decay exponentially. Right? The value of my bank account is hopefully going up, but the value of my car, unless it's a collector car, is absolutely going down from year to year. You know, extra miles, wear and tear, it gets older, the values of cars are going to decrease. There's a lot of things like that happen. But that right there is our percent growth and decay formula that really has three pieces. What are we starting with? How fast is it going up or going down? And how much time are we going to let pass while that happens? Because what we should be able to do, because this question we can almost answer without it, is to make sure that we can get there with this formula. I'm just rewriting it, so it's right here. I want to fill in some pieces. The first thing that I would like to do is come up with a formula in general that doesn't include time yet. Because maybe it's, okay, how much do I have after 1 year? How much do I have after 3 years? How much do I have after 5 years? How much do I have after 20 years? Maybe that's going to change. And so what I would like to do is leave this, and so this is how I'm going to phrase it. Part A, let's say, is write. Let's see, how should we say this? Like, let's write a model in terms of t, like leaving t as t, for this scenario. I don't know, I'm just making it up. Like, don't change t yet. Let's just call it a t. Meaning that this t up here is just still going to be t. But I want to drop in a number for p, for our principal. And I want to drop in an r, a rate, as a decimal. So if this was our situation, maybe we just haven't asked this question. I got $1,000. I'm going to drop it into an account, and it's going to earn me 5% interest. And by the way, you find an account that's earning you 5% interest, you take it. That is, it doesn't sound like a lot. That is huge, huge return. For any investment.
5%.
With no risk? That's crazy. Yeah, 5% is huge with no risk. Yeah. Has anybody seen the movie Boiler Room? Oh, we might watch that. We got some downtime. Ooh, that's good. It is rated R, I think. So I will have to make sure we're all good with that. But it's about an investment firm outside of New York City. It's real good. It's got some Boiler Room. Boiler Room. It's like early 2000s.
Is it about like
it's got Vin Diesel.
guy like joins like the top of the floor with like a different story and like he creates like a route.
No, it's different. It's so good. I have the movie. I don't know if it's streaming anywhere. I'll see if I can find it streaming. I'll let you guys know. But let's just do it. So what's P? What's our principal in this scenario? What is our starting amount? That's principal. That's $1,000. And I don't need a dollar symbol. Just put it down. Okay. The number one is just the number one. The question we have to decide on is, should we put plus or should we put minus? If we are earning 5% interest per year, plus we're going up. I want to make more money. So it's guaranteed to be growth because look, we're going to take 1 and we're going to add a number to it. If I take 1 and add a number to it, I'm going to be bigger than 1. That's all. To be growth, I got to be bigger than 1. To be decay, I got to be less. So that's why we start at 1 and adjust up or down. Okay, what was again 5% of the decimal? Think 5. Don't think 5%. Think 5 cents, like dollars and cents. $0 and 5 cents. Good. And then the T goes up. Yes, go ahead.
Is the 0 before the decimal necessary?
No, but I like it because sometimes the decimal can kind of get lost. Like we're writing in pencil and we're taking pictures of stuff. And I would hate for you to miss the decimal because you wrote it like this and you thought it was like a smudge or like a piece of eraser left over or something. So my suggestion is anytime you've got a number stuck between like -1 and 1, so 0 point something, I always put the leading 0 just to be safe. But you're right, it is not necessary. So if you know you're good, then you're good. Now, okay, what is, not that we have to do this, but what is 1 plus 0.5? This is 0.05. 1 plus that. Put those two together. 1.05. And so sometimes it's written like 1 plus or 1 minus. Sometimes they'll just do it. Right? Sometimes they'll put those together, but these are the same thing. Okay, now we can ask the question. So call this like B. How much money, let's say, do I have after 1 year? Well, now it's not just any A of t. How much time are we letting pass? 1 year. So what we're going to find is A of 1. Right? F of x, same kind of, we say it the same way out loud. A of 1. And what we can do is I can use this formula 1000, and I'm just going to put 1.05 to the first. This t and this t will be whatever that number is. This is just function notation, so I know what I'm doing, and that there's a spot to put. Which, of course, we already figured out. Now I can use a dollar sign because I got my final answer, $1,050. That is not $1,050. The word "and" with money comes out the decimal. Okay? 1,050, not 1,050. If we had like dollars and cents, that would be something else. Then we could say "and." Yeah, even.
On top of that, what about if you didn't want anything from it?
Let's do it. Part C. Let's say we don't touch this money. Here's the problem with that question, Ethan. When we do this formula doesn't account for me leaving the money in there. So what we're going to have to do is adjust this formula to say, listen, if you're going to pay me, let's say once a year, you drop that $50 in my account, Chase or Wells Fargo, Bank of America, whatever you got, they're going to pay me interest on my interest, right? I'm going to make more than just 5% per year because they're going to drop the money in and I'm going to get paid on it. We have to actually adjust this formula to deal with that. Can we do that tomorrow? Can we just say, all right, you know what, no matter what, I never actually get this money into my account until the time is up?
Yeah.
Because if we're talking about actual money, right, dropping money into a bank account and getting paid out, and I don't get paid once a year, my bank account, I get paid once a month. My banks will pay you your interest once a month. Now, if I make my money and the money goes in, now when they calculate my starting amount, like what am I at the next year? It's actually not $1,000. It's however much more I made. So if I had $1,050 in there, now I'm getting 5% on $1,050, which is more than 5% on 1,000. But we need a slightly fancier
5%
over and over and over again. Yeah, so you're going to get paid. And that's why investing, and that's why keeping your money in a bank or finding a way to make money on your money is the way to be. For sure, right? You don't keep money under your pillow. That's not going to work out.
Other than just keep going for 5% on 1,000 and 5% on 1,050.
And then 5% on whatever that is, and then 5%. So it's called compounding interest, and we're going to do it tomorrow.
Mm-hmm.
Yeah, sure. And so let's not consider compound interest just yet. Let's just make sure that we can write the formula for A of 5 rather than A of 1. And what this formula does, it doesn't compound interest, but it can keep track of that 5%, so 1.05 to the 5th. And let's see what we get. of the nice thing about this formula, although it's not going to work for everything, right? It doesn't work for what's called compound interest. We'll do that tomorrow. It does work for things that are just going to kind of grow over a period of time and not change as we go. That $1,000 doesn't change. The 5% doesn't change. So somebody help me out. Plug this in. Like jump into your calculator. Type 1,000 parentheses 1.05 parentheses to the fifth, and let's see what we get. 1,000.
276.
Any cents? Or is this exact? 30 cents exactly?
No.
Keep going. So 1276.28 all the way there, and then it stops. Keeps going. But let's think about it. This is dollars and cents. How many decimal places do we always round to when we're talking about money? Dollars and cents is going to stop right there. And so this is approximately that squiggly looking equal sign is what we're going to use instead of a straight equal sign. We're going to squiggle it out when we're talking about rounding 1,276 and how many cents? 28 cents. That is what's sitting in your bank account. Now, all you have to do is leave it.
That's in 5 years?
5 years.
Oh.
$276.
You
want to do 15%?
Yeah, because that's the average of the Dow Jones.
Let's do it. New problem. Question number 2. Okay. Let's beef it up a little bit. Let's say we started with 10 grand. At 15% interest per year. So we start with 10 grand. Now this is not compound interest. We are not getting paid until the end, okay? Which is unrealistic, but it's going to help you kind of get into this percent growth in the year. Because we talk about like population growth or whatever, that is kind of calculated into the problem. So let's come up with a formula first. Let's do a model in terms of t. So A of t equals. Let's do a model. A of t equals. What's the P stand for again? And what does that mean though? Starting amount. So what are we starting with? 10,000. Right? What's always right after the parentheses in the formula? Not yet. Like as soon as I open just the number 1. 1. Now we got to pick plus or minus. Plus, we're going up. I want to earn some money. Okay, cool. Now we need the rate. 15% as a decimal. 15 cents. 15 cents is 0.15. And for now, it's just to the t. We haven't plugged anything in yet. But now we can ask the question, okay, how much money do we have after, I don't know, let's just mix it. We'll go with 5 years, see the difference. After 5 years. We'll just do this one. So now it's not A of t anymore. Now it's A of 5. Now I actually have a number to plug in. And the thing that I want to see first is you just drop that number into the formula. And hey, if you want, you can call it 1.15. That's cool. And then up here in the exponent goes that 5. Got enough zeros here. Let me help you out. 10,000 times 1.15 to the power of 5. Not going to round yet. I'm going to get a whole bunch of decimals. I have no idea. Help me out. Press button. 1856, blah, 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 blah. How many decimals? Always money? 2, right there. So when we round with that approximately equal to sign, okay, so $12,762 and, well, this is 18 cents right here, but the next number after that's a 5.
So how does it go from 0.15 to 1.15?
Because it's 1 plus or minus whatever your rate was. So I just took these two numbers, the 1 and the 0.15, and I added them together. So that when we look inside at our base, it's just one number, rather than two different numbers being added together. So should this stay 18 cents, or should we jump it up to 19? Jump it up to 19 cents. Now, here's the problem. As nice as it would be to get that extra half a penny, you think the bank's just going to be giving out half pennies? When the bank is calculating how much money to give you, they will always round down. But the other side of that, when they give you like a loan, let's take a car or student loans or for a house, you think they're ever gonna round down? They're always gonna round up. Okay? Which is frustrating. But that's the reality. It's a business. It's all about the money. For us in here, okay, we'll just follow the rules of rounding. We won't kind of contemplate the moral and ethical obligations of which direction to round. We'll just round according to the rules of rounding. But there we go. So 5 years at 15%, you're making 2,700 plus. Pretty good. Pretty good. And that's what that bigger interest rate can do. As we make this base get bigger and bigger and bigger, you're going to see that that exponential growth is really going to take off. Big time. But it's not just about money. It doesn't have to be. It does not just have to be about money. When we talk about things growing and shrinking, whatever, well, money is usually a pretty good example that we can kind of wrap our heads around, and it makes a lot of sense. So a lot of what I think we'll do with percent growth and decay will be about money, but it won't be about interest. It'll be about value. My car is worth. My house is worth. My stamp collection is worth. My laptop is worth. My shoes are worth. Things like that. There's value attached to objects. And that's a lot of the percent growth and decay that we're going to see, or population. That could be population of people, it could be population of animals, it could be things like that. So let's do one example like that and we'll call it. But we doing okay so far? Now, here's the tricky part, right? This is one of 3 formulas. Okay? Percent growth and decay is the first one. Then we'll have compound interest, which will have more to it. Okay? And then there's one that we kind of build from compound interest to get to here. And I'll explain that one in, I don't know, maybe later this week, maybe next week. Okay, let's just do one more. I'm gonna erase some stuff, but I think we got a pretty good start today, which is awesome. We got a formula now, we can use it. Let's use one that has nothing to do with money. Because as easy as it is to understand money, a lot of times things that we deal with don't have anything to do with it. All right, let's create it right. Where's my blue? All right, so 1, 2, call this one number 3. Let's do it. Let's do a population one. The population of, let's try it. Parker, Colorado is, anybody know?
What's the population of Parker, Colorado?
As of 2019, the population of Boulder was
Oh,
105,600.
that's not what I know. What is the population of Parker, Colorado?
What do you guys think? 10,000, 20,000,
Just do it then.
5,000?
I'm gonna ask Google.
1,700.
How much?
57,706.
57,706.
Uninstall search. You're so overpopulated.
Okay. Let's say let's see, how should we say this? The population increases, let's say that, at a rate of, what do you think? What's a reasonable rate of increase? So we want a percent increase here. What do you think? Less than 1%, you think? So you think every year less than 500 people move to Parker? Or is it more than that? Maybe a little bit more than that. How about this? Let's call it 2%. It's not bad. Let's call it 2%. 2%. All right, question A. Write a model in terms of t. Right, when I say in terms of t, that means there better be a t in this equation. Don't put any numbers in for t yet. Let's just call it a of t. Just so we got something to work with, so when we answer the next questions, t will change as we go. And you'll see, gosh, I don't know when, a couple weeks from now, I guess. When I say all these things, and I say the population is now 65,000, how many years did it take to do that? We can answer that question. We don't know how to do that yet. All right, so what's our starting number? What's P?
57706.
There it is, right? Your principal is your starting amount, so that 57,706. What comes right after we open up the parentheses? The number 1. Should we go up or down? Increases. You're looking for words like that. And tomorrow we'll add some options that'll give you increasing and decreasing. All right, now we need a rate as a decimal. 2%. I wish there was a percent button in my calculator. There isn't, so I need the decimal. So what's 2%? 2 cents, right? $0.02. I'll just leave it to you. Now we can answer the question, what is the population? Let's say 1 year later. Now it's not A of t. What's time? 1. And here's the thing that they have to tell us. At a rate of 2% per year. They don't tell us that. We're going to assume it's every year, but it could have been months per month. That could change things. So A of 1, 57706. You can leave them separated. 1 plus 0.02. That's cool to the first. Type that in. Somebody help me out. 57706 times 1 plus 0.02 to the first. And of course, that exponent isn't going to change anything, so you can kind of leave it off. 2% of 57. It should only really be like 1,000 people over there, something like that, a little over that. Press the button, tell me what you get. I don't know, so we should be at like 58, 59. Yeah. What do you say?
58,860.12.
58,860.12. Okay. Was there more decimals after this?
No, that's it.
Just like that? Okay, perfect. Now, with money, yeah, rounding to 2 decimal places makes sense. Dollars and cents. We talking about money? These are people. What do you think would be a reasonable spot to round to? 2 decimal places, 1 decimal place. What? These are living people. Yeah, whole numbers only. If we're talking about things that are alive, rounding to decimals doesn't make any sense. We are going to round to the nearest whole number, 58,860.
Have half a person.
Right? Come on. And there we go. We will build from there tomorrow. Now we got a percent growth and decay. Hopefully I'll give you a chance to practice with some of that. We'll get into some decreasing stuff too, so you see what that looks like. But this formula for sure is going to be a big one for us, and we're going to use it to come up with the compound interest one. We're going to use it to come up with more. It's going to be great. We're good. I will catch you all tomorrow. We got